Alright, today we're doing scientific notation. Alright, here's what it looks like in standard form. This is 3.5 million. And they've come up with a way to represent big numbers in a smaller way, because when you get past millions and billions and trillions and huge numbers, like the speed of light and things like Avogadro's number, things that are either really big or really small, they need a better way of writing them. So they came up with scientific notation. Right? How you express numbers in standard form, right, is there's always a decimal behind the first number, and you can see that here, decimal behind the first number. So here, this needs to be 2.0, and you times it to a power of 10. The only thing you really have to, well, which we've already done, right? So we're going the opposite direction. So here it's 2.0, so I need to move it 3 places. I look at my power, I move it 3 places. So 1, 2, 3. So 1, 2, 3. That means I'm going to add a total of 3 zeros to this 2. Right? It's not always going to be the same number of zeros as your exponent, but it is here. Right? And I'm going to rewrite this just without the deals. This is 2,000. So 2 times 10 to the third is written as 2,000. That's that in standard form. Okay, any questions about that? So you just move the decimal place. If it's a positive, you're moving it to the right. You're making this a bigger number, so you go 3 decimal places to the right. Alright, write these two numbers down. Here you got 6.8 times 10 to the fifth. That means I'm going to move the decimal 5 places to the right. So I go 1, 2, 3, 4, 5. All right. That means I'm just going to add 4 zeros to this. So this is 680,000. It's the same thing as 6.8 times 10 to the fifth. Right? Here, if you've got a negative exponent, you don't go to the right, you go instead the opposite direction to the left. So I go 4 places to the left. So I go 1, 2, 3, 4. That means I'm going to add 3 zeros to this. 0.000325. And that's how you do it. That's how you go from scientific notation to standard form. Any questions? Alright, write this down. Now for writing a number in scientific form, what I do is I put a decimal behind the first number. Here for 4 million, it's just 4.0. Right? And I write any significant number. Zeros are what we call insignificant. So I write any number that's significant. That's not insignificant, which are just zeros. So 4.0, I don't have to write anything else other than times 10 to the, and I figure out the power based on how many times I had to move the decimal. So I know I need the decimal here, so I count how many times I had to move the decimal. So 1, 2, 3, 4, 5, 6. So that's the exponent I write it to. I moved it 6 times, so I raise it to the 6th power. Any questions about that? 5,800, I had to move the decimal 3 times to get it between 5 and 8. So times 10 to the third. Here, 0.072, I'm making a small number larger, so I got to have a negative exponent. Since I'm going to the right instead of left, right, I'm going to make this 7.2 times 10 to the negative 2. Now I had to move it 2 places, but I moved it 2 to the right. And I made a small number larger, so it's got to be a negative exponent. Okay. Any questions? All right, write this down. So here, now these numbers are based off of a word problem that gives in the examples. It says that scientists estimate that there are over 3.5 times 10 to the 6 ants per acre in the Amazon rainforest. So 3.5 million ants per acre. And it says that they estimate that it covers approximately 1 billion acres. The Amazon rainforest covers about 1 billion acres. So we want to find out the total number of ants in that rainforest. So I'm just multiplying 3.5 million times 1 billion. So here they are in scientific notation. It's easy to work with when they're in scientific notation for multiply and divide. Because all I do is I take these two numbers and I times them. And then I take the powers of 10 and multiply them. And because we know what to do when we multiply powers. 3.5 times 1 is just 3.5 times 10. The only thing you got to do is you got to figure out what 10 to the 6 times 10 to the 9th is. Well, when I multiply bases, I do what to the exponents? I add. So 6 plus 9 is 17. So there's your answer. 3.5 times 10 to the 17. That's how many ants are in the Amazon rainforest, or at least the approximation. Now, there's a couple things. If they get, now it says write it in scientific notation. What if you got 0.35 times 10 to the, or that's not 17. It's 15, right? That's Ben's fault. What if I got 0.35 times 10 to the 15? Is this scientific notation? You don't have to write this down, but just pay attention. 0.35 times 10 to the 15. Is that scientific notation? No, scientific notation always has a decimal behind the first number. So I have to move it one. So what would I write now? Would it stay 15? No, I moved it one to the right. I made a small number larger, so it would actually, so I would subtract 1 from 15 and then get 14. Right? Or if I had this, 35 times 10 to the 15. Is this scientific notation? No, so I move it here. So now I got 3.5 times 10 to the 16. I would add 1. Okay? Now that sometimes confuses people, having to move 1. So here's my suggestion. If that confuses you, what you could do, if you have a 0.35 times 10 to the 15, what you could do is write that out in standard form. Okay? Not that hard to do. You know how to do that. So you move the decimal 15 times to the right. Now that's in standard form, you can actually write it in scientific notation. So you would move it 14 places back. It would be in scientific notation. So then you would know what exponent you had to have. A little extra work, but some people get confused by the moving 1 and subtracting, or moving it to the left and adding. So if that confuses you, write it out in standard form, then rewrite it in scientific notation. Okay? It'll be a different number. The exponent would be. Okay? Any questions how to do that? All right, they might give you this. Here they give you a word problem, and it says that a fruit fly, or 1 times 10 to the 6 fruit flies, so 1 million fruit flies, weighs a total of 1.3 times 10 to the 2 pounds. So 130 pounds. All right. How much does one fruit fly weigh? So you have to divide these two numbers. You take the total amount of fruit flies, you're dividing it by how much they weigh. So again, when you're multiplying and dividing, it's easy. You just take these two numbers, so 1.3 divided by 1. You times it by the powers of 10 being divided, so you got 2 divided by 6. What's 1.3 divided by 1? 1.3 times 10. I got to figure out what power. So if I divide bases, what do I do to exponents? Subtract. 2 minus 6 is -4. So each fruit fly weighs that much. 1.3 times 10 to the -4th, which would be pounds. And so they don't weigh very much, do they? Any questions how to do that? Now, there's a couple things I want to point out. When you're multiplying and dividing, this is the way to do it. Easy. You can leave it in scientific notation. If you have to add or subtract, there's not really any shortcut. There's not really any way of doing it other than this, and that's writing it out in standard form, doing the addition or subtraction, and then going back to scientific notation. Okay? That's the only real way of being able to do it. Yeah? All right, here's what you need to do. This is the geological time period. These are some periods in that geological time period with how many years ago that they are. What you need to do is you need to order these in your notes from oldest to youngest. So you don't have to write all this, but you do need to write the oldest one. So if you were to think Triassic was the oldest, you'd write Triassic. Beside it, I want you to write how many number of years ago it was, so you know why you picked it as the oldest. And then if you think Tertiary is the next oldest, then write Tertiary and 6.64 times 10 to the 7th, and so on. So if you thought it was in this order, write it in that order. Right? Write it in however order you want, as long as you think it's oldest to youngest. So go ahead and order these time periods. Order the time periods in oldest to youngest. The first thing I do when comparing numbers, and I look at exponents. And I look, since the oldest would be the biggest exponent, I look, tertiary would be eliminated because it has an exponent of 7, and these have an exponent of 8. So these are going to be much bigger than this. So tertiary is my youngest. So I can go ahead and write that as 4 because it's the youngest. And then what I do is if you have same exponents, like here's 8 and here's 8 and here's 8, then you just look at the factors, the numbers out in front. Is 2.08 bigger than 4.38? No, it's not. Is 4.38 bigger than 2.45? Yes, so Silurian is the oldest. It's got the biggest number. Then look, is 2.08 bigger than 2.45? No, so Triassic is the second oldest. That would leave your Jurassic as the third oldest and Tertiary as the youngest. Any questions how to do that? Right. They will try and get you with this. Obviously, guys, they're gonna make it look easy. They're gonna make you think, oh, this is how it is, and it's not. Okay. There's always something else. Right? Everything should always be kind of suspicious to me. Like, that's a little too easy. Like maybe there's something else I got to do. Maybe there's one extra step or something like that. Which in this case is look at exponents first. All right. Here's your assignment for today.